Today we're going to talk about valence bond theory. Valence bond theory treats a chemical bond as being the overlap of half-filled atomic orbitals. And this is I think this is my favorite bonding model. It is more complex than Lewis theory, but it explains things so much more. And it's still quite visual, so I think it's a lot easier to understand. Molecular orbital theory, ugh. So we're only going to do a little bit of that. But I want you to really pay attention today and try to understand as we go along. So when the first thing we talk about, if you don't understand, you should ask questions. Because if you have questions, then somebody else, probably half the class, has questions as well. Okay? So, Lewis model, obviously an oversimplification. More advanced theories use quantum mechanics, and that involves a lot of math. Those quantitative approaches can predict a lot of properties of molecules, bond length, strength, geometries, dipole moments, and stuff. So we're going to look at two of the more advanced theories, just one today, but in a qualitative manner, meaning we're not going to be looking at numbers, we're going to be talking about ideas. So, we have learned that electrons reside in quantum mechanical orbitals that are localized on individual atoms. So this is what we've learned previously. We learned about the s, p, d, and f orbitals and their shapes. So in valence bond theory, what we do is we say, well, those atomic orbitals might change when this atom becomes part of a molecule. And we call that hybridization. So taking two or more atomic orbitals, the ones we've learned about, and hybridizing them together. So when two atoms approach each other, we've got the electrons and nucleus of one atom interacting with the electrons in the nucleus of the other atom. And if the interactions result in a lowering of the energy of the system, a chemical bond will form. And that's what valence bond theory is looking at. So here is a graph illustrating that. So this is energy increasing up here, and this is the distance between these two hydrogen atoms increasing to the right. So if we think about taking these two hydrogen atoms and we start bringing them together, as we bring them together, the energy of the system, the two atoms, decreases because they begin sharing electrons. They begin forming a bond. And so, it's like two people meeting each other. And as you get closer, you're like, oh, yeah, I like this person, and you get to know them a little better. And you get closer and closer. And then you get to this sweet spot, right, with maximum attraction. And then if you keep getting closer, you're like, oh, no, this is one of those close talkers, right? They're like in my face. This is not okay. And then you're repelled, right? So these atoms get closer and closer, but they don't want to be too close. So we have this sweet spot here, and the energy there is the bond energy, and the distance between those is the bond length. So what's happening here, the blue fuzziness here, is representing the s orbital with an electron in it. And so as these atoms approach, their orbitals overlap, and the electrons in those orbitals can spin pair and become a bond. So we're talking generally about a half-filled orbital from each atom overlapping together. So we have one electron from each atom in this overlap of orbitals, and that gives us a pair of electrons. And just like electrons in atomic orbitals, they're going to spin pair, so we have one, like the one arrow up and the one arrow down, because otherwise two negative things can't occupy the same space. It is possible for one atom to give 2 electrons and another atom no electrons. Okay, that's like, charity. Like, you don't have anything to share, but I'm going to share with you anyway. That's called a coordinate covalent bond, and we're not going to really do anything with those in 1A. So this is a summary. Valence electrons are in quantum mechanical orbitals. The chemical bond is a result of the overlap of 2 half-filled orbitals, and the geometry of the overlapping orbitals determines the shape of the molecule. So all of that so far is probably just words. So this is the part we need to start really understanding. So here's the idea. So here we have sulfur. This is the orbital diagram for the valence electrons of sulfur. And we see that sulfur has a half-filled p orbital and another half-filled p orbital, right? And if we look at hydrogen, hydrogen has a half-filled 1s orbital, right? So we're going to take this half-filled orbital that sulfur has, and it's going to overlap with hydrogen's half-filled orbital, and so we're going to get a pair of electrons in there, and that's the bond. This orbital here is not bonding to anything. That is a lone pair of electrons. And this half-filled orbital can bond with that hydrogen. So we've got one of these electrons is from sulfur and one is from hydrogen. The orbitals overlap, and now we have a pair of electrons in this overlapping orbital. Any questions about that? So we always need to compare what our model is saying to reality. So valence bond theory would predict that this angle here is 90 degrees because the angles of the p orbitals are 90 degrees. The actual bond angle is 92. That's pretty close, right? Vesper theory predicts that it's less than 109.5. Well, it is less than 109.5, so that's not a contradiction either. So the answer to the question, what is a chemical bond, will depend on the bonding model you're using. So according to valence bond theory, what is a chemical bond? A lone electron pair, the overlap between half-filled atomic orbitals on 2 atoms, the overlap between filled atomic orbitals on 2 atoms, or a shared electron pair between 2 atoms. It's B. It's the half-filled. We get the overlap of half-filled orbitals, and then we get a pair of electrons. And this, is reminiscent of the Lewis structure where we see the 2 electrons between the atoms. That's the bond, right, involving 2 electrons. This is the definition that Lewis theory would give us, that it's a shared electron pair. But valence bond theory, we're talking about 2 half-filled orbitals, which kind of is the same thing, but kind of not. So let's look at how carbon and hydrogen could interact. So here is valence orbital diagram for carbon. So we have a pair of electrons in the 2s orbital, and then we have 2 half-filled p orbitals. So we think, well, one of those half-filled p orbitals could overlap with hydrogen's half-filled orbital and make a bond. And the other one could overlap with another hydrogen and make a bond. And then there's this one that's not shown on the diagram, on the picture here, because it's empty. It exists, but it's empty, right? So we don't need to draw it. So this is all very nice and everything. This blue part here, that's this lone pair here. But this, again, predicts a bond angle of 90 degrees. And predicts that this formula would be CH2, that carbon would bond with 2 hydrogens. When in reality, we know that carbon and hydrogen, the simplest compound is CH4, and it has a tetrahedral geometry with an angle of 109.5. So this is not matching up, right? Not matching up. Well, so far we've been assuming that the orbitals in the molecule are the same as the orbitals in the individual atoms. But it's not crazy to think that as these atoms come together and their orbitals approach each other, maybe the orbitals are changing in some way as it becomes a molecule. And this is called hybridization. And it's really a mathematical procedure in which we take our regular atomic orbitals, which, remember, what are those? So those are like standing waves, like they're described by a wave function. So we take those wave functions and we kind of average them. We hybridize them. And this is going to correspond more closely to the actual distribution of electrons in the molecules. These orbitals are still localized on atoms, but their shapes and energies are going to be different than the regular ones. Hybrid orbitals are going to minimize the energy by maximizing the orbital overlap. We'll see that these hybrid orbitals are a little more directional on one side of the atom, and so they can overlap better with another atom's orbitals. To hybridize does require energy, so it's only going to happen if you get a payback in energy by this nice stable bond forming. So what we're going to do is we're going to look at hybridization on interior or central atoms, and we're going to assume that the terminal atoms, the ones outside, are not hybridizing. They actually do, but we don't have to think about that. We can get what we need out of this model without thinking about that. So we're only going to look at hybridization of the central atoms. So general statements. The number of standard orbitals is going to equal the number of hybrid orbitals. So if you take 3 regular orbitals and you hybridize them, you're going to end up with 3 hybrid orbitals. So you could call that the law of conservation of orbitals, right? You don't gain or lose orbitals by hybridizing them. The shapes and energies of the standard orbitals that we're putting together, of course, affects the shape and energy of the hybrid orbitals. So exactly which hybridization occurs is rather complicated. So we're not going to do that. Such calculations are beyond the scope of this class. Yeah, way, way, way beyond. So what we're going to do is we're going to use Vesper theory to predict what the hybridization is. Okay, so let's look at this. So if we take a 2s and 3 2p orbitals and we hybridize them, we're going to end up with 4 identical orbitals. They're going to have the same energy. We call them degenerate. And so this is a bit like in the hotel. So this is the S room. That's supposed to be a bed. And next door is the P room. And the P room has 3 beds. Well, that's not very good. So the S room and the P room. So this is the S room. There's one line there because you can put a pair of electrons there. That's like the bed. And here is the P room with 3 orbitals. Each orbital can hold up to 2 electrons. Everybody okay with that? So hybridizing orbitals is like remodeling the rooms in the hotel. So what we're going to do is we're going to look at Vesper theory, and Vesper theory is going to tell us this molecule needs to have 4 hybrid orbitals. And we're like, why? We can't tell you, it's the secret. We just need 4. Make them so, right? So to make 4 orbitals with the same energy, what we're going to do is we're going to take the S room and the P room, and we're going to take down the wall between them. So we're just going to take out this wall. Of course, there's construction costs here, right? There's energy required to do the hybridization. But now we have one big room with 4 beds. So we have 4 orbitals. How can you charge more for one of these beds than the other, right? They're all in the same room. You're going to go in and check to see which one people are sleeping in? You can't do that. These all have the same energy. They're the same price to sleep in. Does that make sense? So because this is an S orbital or an S bed and 3 P orbitals or 3 P beds, this is called an sp3 hybrid. It's an S and 3 Ps, okay? Make sense? So we get this instead. So here's carbon. This is a regular orbital diagram. It's got 4 valence electrons, right? And so we would put 2 here because this is lower energy. And the next 2 would go up there and each take their own bed. Well, now that we've remodeled this, the electrons come in and the first one's going to take this bed and the second one's like, oh, I'm going to take my own bed, and the next one and the next one. So we're going to end up with 4 half-filled orbitals, each of which could make a bond. And remember we talked about carbon likes to make 4 bonds? Any questions? What do those hybrid orbitals look like? So here are the atomic orbitals, the S, and there's 3 different P orbitals. They have this kind of dumbbell shape, and they're just aligned differently in space. So you kind of have to use your imagination here. But if you took these shapes and averaged them together, what you're going to end up with is kind of a lopsided dumbbell. It's not symmetrical anymore, and that has to do with putting that S orbital in there. So it's got a big lobe on one direction and a small lobe in the other direction. And these would be 1, 2, 3, 4 is 4. Be 4 things now arranged around the nucleus, and it's going to spread out in 3-dimensional space just like 4 balloons do. What shape does 4 balloons make? Tetrahedron, right? So these 4 hybrid orbitals are pointing to the corners of a tetrahedron. This drawing here showing all 4 of them together, what we're doing is we're not showing that little stumpy lobe. This is the one that overlaps. You see, this is bigger now. Here it was evenly split, but only one side can overlap. Now one side is bigger, so it can overlap better with another atom's orbitals. Okay. We don't show that little part because, for one thing, it would make this picture really, really complicated, and it's kind of hard enough to look at as it is. And that other little stumpy lobe doesn't contribute much to bonding. Any questions? So we've hybridized those orbitals, and now the orbital diagram is showing 4 equivalent degenerate orbitals. Carbon's 4 electrons can go 1 in each. We have 4 half-filled orbitals. Oh, and the other thing I like here, so this one was blue and these are red. And what happens when you mix blue and red? You get purple, right? So the purple here, those are the hybrid orbitals. So carbon has 4 hybrid orbitals, and they're pointing to the corners of a tetrahedron. They're each half-filled. Each one can overlap with a hydrogen. So if we, look, here's hydrogen's orbital diagram. It has 1 electron in an s orbital. So that's this blue part. So one of these electrons is from hydrogen and one is from carbon. 2 half-filled orbitals overlapping, and now we've got this pair of electrons. Any questions? This works with experimental observations because carbon and hydrogen form CH4, not CH2, and the bond angles are 109.5, and by hybridizing those orbitals, now we get bond angles of 109.5. What about a lone pair? Well, it can handle a lone pair. So let's look at nitrogen. So nitrogen's atomic orbitals, nitrogen has 5 valence electrons, right? So it would be 1, 2, 3, 4, 5. Well, if we're going to hybridize those, we're taking the wall down between the two rooms and we're making them all equivalent. And we, instead of an S or a P room, that's called the sp3. And now when we put 5 electrons in there, we're going to follow Hund's rule. And 1, 2, 3, 4. They're going to each take their own bed until they have to pair up. And number 5 is going to go over there. So this is 4 sp3 hybrid orbitals. One of them has a pair of electrons in it, and the other 3 are half filled. This one with the pair of electrons, that's our lone pair. The half-filled orbitals are going to overlap with hydrogen and form bonds. Any questions? Does it make some sense? So we know that this bond angle is 107 degrees, not 109.5. And in Vesper theory, we talked about how this lone pair takes up more space, is more repulsive. The valence bond theory explanation is that the hybridization is less complete, and so that affects the angles of the hybrid orbitals. That's just in case you were interested why. Okay, how many sp3 hybrid orbitals result from the hybridization of 1 s and 3 p orbitals? How many orbitals are we starting with? 1 s and 3 p. 1 plus 3 is 4. So how many should we end up with? 4. We're going to start and end with the same number of orbitals. So in the hotel, we're rearranging things, we're remodeling, we're building walls or taking walls down. The beds are still there. We're not gaining or losing any beds. We're just kind of changing the room size around them. Well, what if we take the s orbital and hybridize it with only 2 of the p orbitals? Then we will get 3 hybrid orbitals, because we're 1, 2, 3. We're taking 3 atomic orbitals, hybridizing them. We get 3 hybrid orbitals. And then what about this p orbital here that's left? Nothing happens to it. It just stays the same. So let me draw the hotel picture for you. Oops. See that? I need a faster way to draw a bed. I'm just going to call the beds B. So each B is a bed. It takes too long to draw them. So I had the S room with 1 bed, and I had the P room with 3 beds. That's the regular atomic orbitals. So what they're doing there is the customer comes in and says, I need a room with 3 beds, and I want it as cheap as possible. So instead of skipping the S room, we're going to remodel here. We're going to take this wall out, and we're going to put it over here. So this is just the P room. It just only has 1 bed now. And this is SP2. the energy of these, the price to sleep there is between the S and the P. So this is higher than S but lower than P. And this one is just still there. Okay? Nothing happened to it. Well, what would that look like? We're taking an S orbital and two P orbitals, like you throw them in the blender and you bake them and you get this. You get three things, a lot like three balloons. And how would the three balloons arrange themselves? A trigonal planar shape, right? So we can imagine these hybrid orbitals as being like the balloons when we were talking about Vesper theory and the shapes, right? So it's three things trying to separate in space, okay? So this molecule, H2CO, has sp2 hybrid orbitals. I'm just telling you that. So here is the valence orbital diagram for a carbon atom. And we're going to hybridize. So we're going to put these three together and leave this guy out. Now this is a little bit tricky. So when these four electrons then go to occupy these beds, they're going to go 1, 2, 3, and what we learned before is that this guy should pair up over here because these beds are cheaper. Well, this is a hybrid room now. It's closer in cost to the P room. The difference isn't as great. So if it was only like $1 extra a day on a $75 a night room, even a cheapskate might say, well, that's worth it to have my own bed. Because these are so close in energy, this electron can go into this empty orbital instead of pairing up here. Okay? It's just something we kind of have to be okay with. So this is our hybrid orbital scheme for carbon, and then this shows us we have 4 half-filled orbitals again to make bonds. So what's going to happen is one of these is going to overlap with a hydrogen, and there's another hydrogen. I'll put it down here. There's another hydrogen, and one of these can overlap with that. This is in the way. One of these can overlap with a half-filled p orbital from oxygen, and this p orbital can overlap with another p orbital. Okay, so let's see what that looks like. It's balloon art gone bad. Okay, let's try to look at this. So the purple ones here, that's the hybrid orbitals. sp2 was 3 orbitals hybridized, so we got 3 hybrid orbitals. They're now the same as each other. They're just spread out in this trigonal planar shape. Okay, they're each half-filled, so one of them overlaps with hydrogen, another overlaps with hydrogen, and the third one overlaps with one of the half-filled p orbitals on the oxygen. Okay? So how does that other bond happen? So carbon has a half-filled regular old p orbital, and oxygen has a regular old p orbital that's half-filled. Oxygen also has a lone pair in the s and a lone pair in a p orbital. We're just not showing those on here because it gets kind of crowded. So these p orbitals, they're parallel to each other, so they can't overlap end to end. We can't shift them or rearrange them or anything. That's just their position relative to this bond. So what do? So they are trying to reach around to each other. So imagine that's the other half filled p orbital, and I'm trying to reach around. It's kind of a sideways thing to overlap. It's not as good. And both the top and the bottom are going to do that. Oh, I wonder how many drops of the pencil I have left before it dies. So this orbital is kind of stretching around to try to overlap with this one, which is kind of coming out to meet it, right? And it does that on the top and the bottom. The thing that's kind of hard to remember is both sides of this are the same orbital. They're not two different orbitals. It's one orbital. So this end overlaps with this end of the other one, and these ends overlap. And so this red part here is one bond with one pair of electrons in it. Okay? So these are two different kinds of bonds. This end-to-end overlap is called a sigma bond, and this side-to-side business is called a pi bond. Turn your head sideways. Greek letter pi? Yeah? So taking these guys apart and looking at these different kinds of bonds. So the sigma bond, we have the ends of the orbitals overlapping. And this could be hybrid orbitals doing this, or it could be unhybridized orbitals doing this. So here we're just showing two p orbitals overlapping with each other, and they're going to make this sigma bond. Now, if you imagine yourself, well, that would be a little too high. If you imagine yourself looking down this column, right, what are you going to see? You're just going to see red circle, right? Because it goes in and out and in and out, but it's circular, right? Like the letter sigma is round, okay? The pi bond is when you have these two that are parallel to each other, and they're going to, like I said, kind of bend and stretch towards each other to overlap that way. That one's not round. This is the pi bond. Okay? Do you see how those two different kinds of overlaps are different? This one's better, this one's stronger, this one's weaker. So we can label those bonds, and this is something that you'll need to do on worksheet 11, okay? So labeling these bonds, the first thing we're going to do is, well, what kind of overlap is this? Well, this is sigma, end to end. So that bond is called sigma, and then a colon, and then we're telling which two elements are involved in that bond and what orbitals they're using. So this is a bond between carbon, and carbon is using an sp2 hybrid orbital here. And that's overlapping with oxygen, and oxygen is a terminal atom, so we're not considering hybridization on that. It's using one of its regular p orbitals. We can also describe the bonds between hydrogen and carbon. Hydrogen's using an s orbital, which doesn't really have an end, but it's the end of the sp2 orbital that's overlapping with it, so it's still a sigma bond, and it would still be, symmetrical. So this would be sigma between carbon using an sp2 hybrid orbital and hydrogen using an s orbital. So this description would apply to both of these. They have the same description. It's a sigma bond between an sp2 orbital on carbon and an s orbital on hydrogen. And then this one, remember the top and the bottom, I know it looks like two bonds, it's one, it's just one bond. Just tell yourself it's only one bond. This one bond here is that side-to-side business, right? Pi. Oops, did not mean to do that. So this is the pi bond, and this is between carbon and oxygen, but this is between a p orbital on carbon and a p orbital on oxygen. Because if we go back and look at this, when carbon hybridized, it had a p orbital that was left intact, just unchanged. And it put one electron in each of those. And so this is the one that does the pi overlap with one of these oxygens, p orbitals. And these three guys are going to go sigma bond, ending, the end will overlap with this guy. There's two hydrogens, and with one of the p orbitals from oxygen. Any questions? A lot of kind of blank faces. Not sure what to make of that. So we get more insight or understanding using valence bond theory compared to the Lewis model. So what we're just looking at is that a double bond between carbon and oxygen actually has two different kinds of bonds, right? So whenever we see a double bond in a Lewis model, in valence bond theory, that's going to correspond to one sigma bond, the end-to-end, and one pi bond. The pi bonds are always going to be between p orbitals. Pi bonds, p orbitals. And we see that those pi bonds are weaker because the side-to-side overlap isn't very good. It's not very efficient. So those are easier to break. Those bonds are weaker. And the sigma bond is the stronger bond. Okay? Another thing we learn that matches up with experiment is about rotation of bonds. So here we have this molecule, and it has a single bond between carbon and hydrogen. And so we can look at the hybrid orbitals, etc. And here we've got sp3 hybrid orbitals, and they're making sigma bonds. Sigma bonds are single bonds. Single bonds are sigma bonds. Okay? So it's making single bonds with two hydrogens, with a chlorine, and with this carbon. This sigma bond is symmetrical. So, put your two fingers together and you can rotate your hands, right? This is a model of that compound. And it can spin around that single bond because that bond is symmetrical. If we put a double bond, now we've got the double bond is a sigma bond plus a pi bond. This thing is going to restrict the motion, right? That's like taking two fingers and putting them together. Can you rotate your hand now? Not without breaking the bond between your fingers. So that's like this guy. A double bond won't rotate anymore. And this is true to observation. This is looking at it with space filling models. I've got the ball and stick models here. So here we've got the free rotation around that single bond. And here, because there's no rotation around that bond, these are actually two different compounds. This one, I happen to have the model here because I did this second last night, has the chlorines on opposite sides of the double bond. The trans means across, right? So these are on the opposite side. That's the trans isomer. And here, these are on the same side. And to make the change from one to the other, you actually have to break some bonds. Now the two chlorines are on the same side. And that's called cis, C-I-S. If, like me, you're fond of your sister, my sister and I, we're on the same side, right? There, we're on the same side. This is cis, and that's trans. Any questions? Do a lot of stuff like this in OChem. So in section 1010, we learned that double bonds are stronger and shorter than single bonds. Specifically, a carbon-carbon single bond has an energy of about 347 kilojoules per mole. A carbon-carbon double bond has an average energy of 611. So if it's a double bond, why is the energy not twice as much as a single bond? So, 347 times 2 would be 694. So why is the double bond not 694 kilojoules per mole? Because those two bonds aren't the same, are they? If you were making two sigma bonds, which you can't because it's impossible, if you had two bonds that had the same energy, then the double bond should be twice as strong, right? But the double bond is one strong bond and one not quite as strong bond. So instead of this times 2, we've got this plus something less than that. And so we're getting 611. So which is the correct answer here, A, B, or C? A. Because in valence bond theory, a double bond is actually two different kinds of bonds. A sigma and a pi, they don't have the same energy. Well, we can also hybridize just two orbitals, the s and one of the p's. And so then we end up with two hybrid orbitals. So these in the box, these get hybridized. Their energy is going to be between these two. And then the other two orbitals are just there, unchanged, unhybridized p orbitals. And so this is called an sp hybrid because it's one s and one p. This one's a little easier to visualize, the averaging of these two shapes. So we're taking this and averaging it with that. And so we end up with two of these shapes. All these hybrid orbitals have roughly the same shape, right? They're just going to have different orientations. Their sizes might be a little bit different, but we don't need to be concerned with that. So they've got a big lobe and a small lobe. And so they're going to point in opposite directions. If we show them together minus their little stumpy lobes, this is what we have. Like two balloons, it even looks like two balloons tied together. They're going to be across from each other. Where are the unhybridized p orbitals? Well, we're using the one along the x-axis to hybridize, and so this is going to be along the x-axis. The unhybridized ones, there's going to be one along the y-axis, so there's going to be one going up and down, and one along the z-axis, which is in and out of the screen. So it's a little bit silly. They say draw the Lewis structure. Well, that is almost the Lewis structure. There's the Lewis structure. If we look at this carbon, it has two electron groups. it turns out that we can look at VSEPR theory, counting the electron groups, and that can tell us how many hybrid orbitals we need. So this is 2 electron groups. It's not a very good S. I'm left-handed, this doesn't work very well. Good enough. So, looking with the view of VSEPR theory, electron groups, I look at this carbon and see it has 2 electron groups. So that tells me I need to hybridize an S and a P. I need 2 orbitals hybridized and I get an sp hybrid orbital. So that's what we're doing here, is we're taking these 2 and making sp, and then we've got these p orbitals that are left unchanged. And again, the energy difference between these 2 is small enough that they're going to fill them singly instead of pairing up. So again, we have 4 half-filled orbitals to make 4 bonds. So this is what it looks like. Here's our carbon. There's one sp orbital, and here's the other sp orbital. So one of them overlaps with the hydrogen, and that's this single bond over here. The other hybrid overlaps with a hybrid from this carbon. This molecule has 2 interior atoms, right? So we're going to consider the hybridization for both of them. Hydrogen is a terminal atom, it's not going to hybridize. So this carbon also has 2 sp orbitals. One overlaps with hydrogen and the other overlaps with carbon. So we have a sigma bond here between carbon sp and carbon sp. These are a sigma bond between carbon sp and hydrogen s. And then we have those 2 unhybridized orbitals, right? There's the one going up and down. Well, the other carbon has one like that as well. And so those can overlap side to side. That forms the second bond. And then there's this guy along the z-axis, and that can overlap side to side with this one along the z-axis, and that forms a third bond. So there are 3 bonds between the 2 carbons. This is going to be a linear molecule because the sp orbitals are linear. Because you made 2 of them, and 2 balloons are going to go on opposite sides of the nucleus. VSEPR theory also tells us this is going to be linear because we've got two electron groups. Questions? So what's the hybridization of carbon in CO2? This is still going to require drawing Lewis structures. And the point of this is not to review drawing of Lewis structures. Okay, so there's the Lewis structure for CO2. How many electron groups are around the carbon? 2. So what hybridization do we need? sp. sp, we need 2 orbitals, so an s and p. Any questions? We learned about expanded octets, right? We learned that elements in period 3 or larger can do that. In valence bond theory, this corresponds to getting the d orbitals involved. So we have an S room, a P room, and the D room. This has one bed. This has 3 beds. This has 5 beds. These are walls. The third level, period 3, is the first level that has a D room. The second floor, the second period, has S and P only. You can't expand into a D room that doesn't exist. Now, this D room may be empty, but an empty hotel room still exists, right? It's not that it like disappears when nobody's sleeping there. Then maybe you wouldn't have to clean it, I guess, but that's not how things work, right? It's still there, it's just empty. So, if you look at like sulfur or something, sulfur does not have any electrons in its d orbitals, but the d orbitals are there. So we can start moving walls around, taking walls out. So if we need 5 orbitals, so I don't have quite enough fingers for that. So 5 would be 1, 2, 3, 4, 5. This would be a D, I guess. We need to have 1, 2, 3, 4, 5. So we're going to, remodel. We're going to take out some walls. And we're going to put the wall there. Now, this is called SP3D because it's this bed from the S room and 3 beds from the P room and 1 bed from the D room. And these guys over here, just empty beds in an empty room. We just moved a wall over. How do you know that you need 5 beds? You look at the Lewis structure and count the number of electron groups. So if we need 5, we're going to hybridize the S, 3 of the P's, and 1 of the D's. And we're going to get 5 hybrid orbitals. They are the same shape, just different orientation. And so they're going to do what 5 balloons do. Trigonal bipyramid shape. They're going to spread out into that shape. Those unhybridized d orbitals are just going to sit there. So here's an example. So here's the Lewis structure for AS F5. Lewis structure shows us 5 electron groups. To get 5 equivalent orbitals, we hybridize 5 atomic orbitals. That's the S, 3 P's, and a D. And so then we get these 5 equivalent things that make the trigonal bipyramid shape. Each of them is half-filled. Each of them can overlap with the half-filled orbital on fluorine. And if we think about fluorine, that's on the end, so we're not going to hybridize that one. It has 7 valence electrons. It has 1 half-filled orbital. That's why we can say that, fluorine is almost always just going to form 1 bond because it doesn't involve messing around with its electrons to do that. What if you need 6? Well, then you take 2 of the d orbitals. Now you've got 6 things, like 6 balloons. It kind of looks like that, right? So we have these 6 hybrid orbitals, and now we have 3 unhybridized d orbitals just down there at the end of the floor. So SF6, Lewis structure, 6 electron groups. We need to hybridize 6 orbitals, and so those are going to be SP3D2. It's going to make these. And here's fluorine. and its one half-filled p orbital can overlap with this, and so we can have bonds with 6 different fluorines. And so this would be described as a sigma. On the S, it's using an sp3d2 hybrid orbital, and on the fluorine, it's using a regular p orbital. So how do we know which hybridization scheme to use? Well, the rigorous method is very, very involved. You have calculations and all kinds of stuff. So we're going to go for good enough for Chem 1A. We're going to assign the hybridization scheme from the electron geometry of the interior atoms. We're going to look at the number of electron groups. It doesn't work all the time, but it'll work for all the questions on the exam. Okay? So this is an overview of the different hybridized orbitals. And here's the list of instructions of how to do this. First, you have to start with the Lewis structure. And so you're going to have to do this on worksheet 11. So guess what? For all of them, except I think one, you already drew the Lewis structure on worksheet 10. Got the Lewis structure, right? You're going to use Vesper theory to predict the electron geometry. I already had you count the number of electron groups and the number of lone pairs. The number of electron groups tells you how many orbitals you need to hybridize. You always start with S and go through the P's and then into the D's if you need to. Then you're going to sketch the molecule. Always start with the interior or central atom and draw its orbitals, and then you show it overlapping with the other orbitals. I won't make you draw things like that on an exam. Okay. And then you label the bonds. Okay, so let's do an example here. Write a hybridization and bonding scheme for XEF4. Got to start with the Lewis structure. So we've got, well, let's just write this out. We've got xenon with 8 and 4 fluorines each with 7. And so I believe that adds to 36. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Everybody's got an octet. What do I do with the extra electrons? Put them on the central atom. Xenon is in period 5. Xenon has an empty D room that it can expand into. So we'll put those 34, 36 on the xenon. If you don't draw the Lewis structure, if you just look at this, you're going to say, well, it's 4 single bonds. It's going to be tetrahedral, right? Nope. Because how many electron groups is this? 5, right? So sp3d. So hybridization is sp3d. I'm sorry, it's 6. Thank you. Because I can't count. Yeah, it's 6. 1, 2, 3, 4, 5, 6. Thank you. Thank you for catching that before I started drawing things. Okay. Drawing these things is challenging. So I'm going to have 6 hybrid orbitals. They're going to be like 6 balloons. So we've got one up here and one down there and one going back and one coming out and one going back and one coming out. And each of these has an electron. Well, you know what? Let's wait a minute on that. So we've got our hybridization. Let's look at 2, 3, 4, 5, 6. Let's look at how the valence electrons for xenon go, right? So if I've got sp3d2, how many d orbitals are left over? 3, because there were 5 of them. And so I took 2 of them to be part of this sp3d2. And these guys are just left. How many valence electrons does xenon have? 8. Oops. That was scary. Well, we're just going to live with that red line. Pretend it's not there. 8 valence electrons. So 1, 2, 3, 4, 5, 6. Do we go up into the D or not? Let's use our Lewis structure here to help us decide that. This thing has 2 lone pairs on it, right? Those are 2 pairs of electrons that are paired up in the atom before it starts overlapping with things. So if I go 1, 2, 3, 4, 5, 6, 7, 8, these are my 2 lone pairs. Okay? So we're actually never going to put electrons in those unhybridized d orbitals, but looking at the number of lone pairs can help you know when to do that. So then what we've got here is we have 2 lone pairs. If one of the lone pairs is on this orbital, where's the other lone pair going to be? On the opposite side, right? Because the lone pairs want to get as far away from each other as they can, which is going to be on opposite sides. And then each of these is going to be half filled. And then these are going to overlap with fluorine. So here's a fluorine, and fluorine's going to use its half-filled p orbital. Oops. You get the idea. That's a p. Weird looking, huh? Do you kind of see how that's happening? Half-filled orbitals overlapping. And then we need to, the bonding scheme is describing the bonds. So what kind of bond is this, sigma or pi? Sigma. Does it look like a pi? Is there, no. Sigma bond, and it is between xenon and fluorine. So it's between xenon and fluorine. What orbital is xenon using? sp3d2, right? The hybrid orbitals, sp3d2. And what orbital is fluorine using? Well, let's draw. So fluorine is going to be unhybridized. Fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. It's this half-filled one that's going to overlap. That's a p orbital, right? All 4 bonds are the same. They all have the same description. So the worksheet is going to ask you to draw things like this and like this, and it's going to ask you to write things like this. It's not going to make you draw the pictures. Okay, let's do this example, and then we'll call it a day. Use valence bond theory to write a hybridization and bonding scheme for CO2. Well, again, we have to start with Lewis structure. Ta-da, Lewis structure. How many groups on the carbon? 2. So what's the hybridization scheme? sp. So if we look at that, we're going to end up, well, actually, let's do it this way. I'm going to start with the atomic orbitals for carbon, and then this is the hybridized. So I'm taking the S and one of the P's, right? Carbon has 4 valence electrons. So this is the hybrid orbital. And this is sp, oh well, and that's D. No, that's not DSP. Don't listen to me. So as I put the 4 electrons in here, 1, 2, you're like, well, you're confusing us now. Do we pair these up or not? Does this carbon have any lone pairs? No, don't pair them up. Stick them over here. These are the 2 that are going to form the pi bonds that are going to make the double bond with this oxygen and the double bond with that oxygen. So this is what carbon looks like. And let's see, I'll put oxygen. Try to sneak it in up here. So oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. It's got these 2 half-filled orbitals. So one of these will overlap with a hybrid orbital and make a sigma bond, and the other will overlap with a p orbital and make a pi bond. So let's see if we can draw that. So here's carbon with its sp orbitals, 1 on each side, two of them like the balloons, right? And so it has 1 electron in each of those. And then what else does it have? It has 2 half-filled p orbitals. So that's 1 orbital. The top and the bottom is 1 orbital, and then the in and out one is another orbital. Okay, so over here we have the oxygen, and oxygen is using p orbitals. One of them is going to overlap with the carbon, sp orbital, and make a sigma bond. The other one that's half filled is at right angles to this one. There's also an s orbital with a lone pair and a p orbital with a lone pair. I'm not going to draw those because it would be really ugly. So this one and this one can overlap side to side. And there's 1 pi bond. Oh, there's another oxygen in this molecule. The other oxygen also has 2 half-filled p orbitals. So one of them is going to overlap end to end with the hybrid orbital of carbon, and then there's another orbital here that's at right angles that can line up with this oxygen's p orbital. So we have a sigma and pi bond, that's the double bond, a sigma and a pi bond, that's the double bond here. So then to label these, this is the sigma bond. It's between carbon and oxygen. What orbital is carbon using? the sp hybrid. The sigma bond is always going to use the hybrid. The hybrids are always going to make sigma bonds. You try it. And what's the oxygen using? The oxygen is just using p orbitals. So that bond description works for this one and for that one. Same kind of orbitals, same kind of atoms. And then we also have this pi bond. The pi bond is also between carbon and oxygen. Pi bonds are always p orbitals because they have to stick out so that we can do that side-to-side business. So this is an overlap between a p orbital on carbon and a p orbital on oxygen. So this could be the pi bond, and this could be the sigma bond. And then you've got another oxygen that's going to overlap in the same way with those other two. Any questions?